In this video, we're going to talk about inverse functions. When we're talking about inverse, basically we're talking about doing a function in reverse. So if I have f of x is equal to y, we can say g of y is equal to x. So, and one of the things we do to denote inverse functions is inverses are denoted by f to the negative 1 of x. But what we do know also in the definition of inverse that if I compose one of the other, so if I have f of the inverse, it should yield me right back to x. Composite function, excuse me. And if you have the composite of the inverse of the parent function, then it also should lead you back into x. So what we're going to do first is we're going to find out if they are in fact inverses of each other. So I want to know if f and g are inverses of each other. So what we're going to do is I'm going to say f of g of x, and I'm going to say g of f of x. If they're true inverses of each other, I should be able to take 4, doing the f of g of x, 4 of x plus 7 over 4. And I should be able to take x plus 7. I forgot to put that one in. Hold on. Forgot to put the function value in there. Taking my g of x, so I have 4. Oops. Did I not get that? Taking 4x minus 7, that's my f of x, putting it into g, and see if I also don't get x. So when we work this one out, forgot to put the rest of the function value. So we have this is 4, it cancels out 4, so we have x plus 7 minus 7, which does become x. And then here we have 4x plus 7 over 7, so we've got 4x over 4, which is equal to x. So when we composed f of g of x or g of f of x, we got x both times. So yes, these two are inverses of each other. Doing the same thing. So this one, we're going to go f of g of x, and we're going to go g of f of x. So put 1 into, we're going to have 3 over, putting that in for x. So this is going to be 3 over x, which does become x. Then I'm going over here, and I'm going to start with my g of x, which is 3 over x, but now I'm going to put in 3 over x minus 4 plus 4 on the outside here. So when we skip, flip, and multiply, we're going to have x minus 4 plus 4, which is also equal to x. Oops, equals x. So yes, when we compose one function into the other, we do have that these are in fact inverses. They have to be equal to x. The composite of each has to equal to x in order for them to be inverse. So what we have to do now is we have to find the inverses. Now we tested it first, now we have to actually find the inverse. So what we do is we switch x and y, and we isolate y again. So if I want to find the inverse of this particular function, we're going to say, remember, f of x is the same as y, but what we're going to do to find the inverse is we're going to have x is equal to 1/3 y plus 4. So comparing this original function to our attempted inverse, all I've done is I've switched the x and y. So now we have to get y by itself. So I've got x minus 4 is equal to 1/3 y. And then again, to get rid of the 1/3, we multiply both sides by 3. So we have y is equal to 3x minus 12. Now the notation of function inverse, I started to say this at the beginning of the video, is f negative 1 of x. So which shows the relationship. If f of x is the original, f to the negative 1 is the inverse. So we can write this appropriately as f negative 1x, or the inverse of f of x, is equal to 3x minus 12. All right, so let's do this again. Remember, g of x, whatever the function notation represents y. So now I have x is equal to 5, we switched x and y. So 5y cubed plus 2. So subtracting 2 dividing by 5, so I've got x minus 2 over 5 is equal to y cubed. And then, of course, we're going to take the cubed root of both sides. So what I have is now g to the negative 1 of x is equal to the cubed root of x minus 2 over 5. One last time, remember the notation is the same as y. So to find the inverse, we switch the x and y. And then we get y by itself, or we isolate y. So I'm going to take the cubed root of both sides to get to get rid of that cube right there. So I've got y plus 6, and then I'm going to subtract 6. So we have the cube root of x, subtracting 6 off the outside is equal to h to the negative 1 of x. So in the next part of the notes, what I have is graphing the functions and their inverse on the coordinate plane. So being that I'm working from my computer here, I'm going to let Desmos help me out here. So I'm looking first at the f. This top one is my function. This bottom one is my inverse. And we're trying to see the relationship between them. And from this vantage point, it's a little bit difficult. So let me see if I can't change my scale a little bit. And it makes it a little bit more even, but it still doesn't help us out a lot. So what I also want to do is I want to put in this line. Now, if you'll notice here, the green line, this is my y is equal to x line. And if you'll notice now, it almost looks like this is kind of mirrored across this line, like if it's reflected over that green line. That's the relationship between the function and its inverse, is that every function is a reflection of over this line. If this was a piece of paper and you folded along that green line, you would get the other side of this line. So let's look at another example that might be a little bit more clear. I'm going to work on to g of x and its inverse. And here's the example of g of x and its inverse. And if you'll notice again, what we have is the green line being my y is equal to x line, and this is a perfect reflection. The red and the blue are reflections over each other. The blue comes up to the red here, the blue goes over the red there. So again, this function and its inverse are a reflection over the y is equal to x line. And here's the last one. Here's h of x. And again, you'll notice the purple and the black reflect exactly across the line of y is equal to x, or that green line. Every inverse is a reflection across the y is equal to x line of its original parent function. The thing I also want to point out is that both of these are functions. When I look at this, if I were to draw a bunch of horizontal lines down the purple, my parent function is a function, as well as the inverse function, right? If let me turn these both off and go back to my g of x. Same thing here. I can zoom in a little bit if I want. But again, this is also a function. Now it looks like that blue might not be a function, but actually what it does is it comes close and close and eventually crosses at 2 and goes on. But it never loops up on itself. It almost looks like it would fail the vertical line test, but both the original and its inverse are both function, and this is what we call one-to-one. One-to-one, that means, remember, for a function, it means for every x, I have exactly one y. But one-to-one means for every one y, I have exactly one x. Or in other words, the inverse is also a function as well. So flipping back to the notes there, all of the functions and their inverses on function, which means it's one-to-one. And what we can do is we can do this by testing. We want to know, the question is, is the inverse of a function also a function? So if I'm looking at these graphs here, first of all, I notice that all of these already are functions, because if I do my originals, I do vertical line tests all day long, I will get these are all a function. And that's great. But once I know it, that afterwards, if I take all these off, that I want to know if I reflect this over the y is equal to x line. So if I take this one thing here and I draw, so I'm reflecting this over this particular line. So I know my inverse is going to look something like this. That's a rough sketch. Or if I'm drawing my y is equal to x line here, that I know my inverse is going to look something like this. Oops, backwards, sorry. I drew it backwards. And that is a terrible sketch, but that kind of gets the idea. And each one of these, if I draw again along here, that means it's now going to come down here, go this way, and come down this way, going across the y is equal to x line. Again, if the y is equal to x line here, I know I'm going to come this way, go down, and go this way. So these are all what the all of these are a basic sketch. I just eyeballed reflecting over the y is equal to x line. But which one of these become functions? Well, this one in A, that's still a function. This one in B, this one is not a function. My original was a function, no problem, but my inverse was not. So we're going to come back to that one. Looks like C doesn't become a function here because this portion here becomes super problematic. Well, let's look at D. D, I think, is okay. I'm drawing all my vertical lines, and that's not a problem at all. So let's see, maybe if I'm not good at eyeballing it, let's see if I can possibly figure out which would be functions. And we said that C and B would not be, their inverse would not be functions. But what we can do is remember when we tested for functions on our original, we did the vertical line test because I was drawing all my x equals, my x equals line. So when we want to test for inverse, we do a horizontal line test. So vertical line test told me whether or not these were all functions. Horizontal line test will tell me whether or not my inverse will be functions. So this one I still passed the horizontal line test, same as the vertical. I only hit the graph once. But this one fails the horizontal line test, and we showed that when I had the inverse sketched on there. That when I hit going side to side, it's the same as hitting it side to side when I actually sketch, or excuse me, up and down when I actually sketch the inverse. Same thing with this one. This one failed the horizontal line test, so the inverse is not a function. My parent or my original function is a function, but the inverse is not, and this one is. So when doing these graphs, make sure you know that which test does which function. So vertical test does the original function, horizontal line test to see if the inverse will be a function.